So good afternoon. Welcome to lecture 9. So having gone through this entire journey of seeing the convergence analysis, etc., we'll quickly conclude our topic of stochastic gradient descent. This doesn't write. Wait a second. Okay. I was just saying that having set a background, we'll now conclude our discussion of stochastic gradient descent. As a homework, I had asked you to just ponder over the table, the general table that I had provided. So basically, we had talked about this general framework of algorithms called adaptive gradient descent. In the last class, I had motivated this entire discussion based on curvature. Okay, but today, based on a very nice blog at rudder.io, I'll take a slightly different perspective. Okay, so motivation in last class. Basically, we had talked about adaptive learning rate, but I said, well, what is the adaptation? Because it was motivated by the curvature. So I talked about what's the general Newton update, right? And I said that this curvature comes coming from the Hessian of the matrix, the matrix of all second order derivatives and mixed partial derivatives, or its surrogates. Okay, very often we have quasi-Newton methods which don't try and get the Hessian, but a surrogate, an approximation. So that's how I had motivated in the last class. But today, I'll be using a different narrative. There's this very nice rudder.io, which doesn't get into the Hessian part, but gives motivation more from accumulating gradient, from the perspective of accumulating gradients in this case. Okay. So a different perspective today. On this side, and the perspective is two things: accumulating gradients and gradient squares. Okay, so accumulating gradients, in some sense, that's what momentum methods do. Okay, so now what gradient squares? I mean, gradient squares, in some sense, is what also is related to the Hessian, the curvature, and therefore the learning rate. Okay, or rather, adaptive learning rate. For which you can also recall our discussion on 4 different Armio conditions. So I'd run you through this Colab notebook also, right? Where is that notebook? This. Here you see Armio conditions. So I'd motivate. It's visible, right? It's too small. Okay, I talked about backtracking, line search, and so on. So this was, and in one of those discussions, I think the version 3, we were also trying to do some interpolation using a polynomial interpolation. You remember? So whenever you see gradient squares, etc., there's some kind of learning rate adaptation based on some interpolation. Okay. So we had seen one motivation. That's not the only one, but the other motivation that has come today is from the perspective of Hessians. Okay, so we'll continue on this discussion. Now, from that perspective, you can think of all of this, right? So gradient square accumulation, which is very closely related to curvature, is what gives rise to adaptive learning rates. That's a kind of connection. So this is a recap, and then we said, well, here's our grand one equation to unify them all. When we say them, we're talking about stochastic gradient descent, heavy ball, Nestor adaptive gradient, momentum, and then add a grad, root mean square accumulation, and then adder. So I had kind of left you at this slide in the last class. Now, one important thing to note is we are dealing largely with all diagonal matrices. So whenever we do inverse, we are basically dividing. Okay, so we don't have to get intimidated by inverse. All inverses, multiplication by matrix inverse, is amounting to what? Division. Right, square of the matrix is basically square of each entries, because we are dealing with diagonal matrix. Okay, diagonal. So yes, you can see that here right up front, diagonal matrix. So multiplication by matrix is inverse is amounting to division, square is the square of each entry, and so on. So now let's understand what are these different methods. Under this grand unification, it's easy for us to understand stochastic gradient descent, where we just have the GT will be an identity, and because of that, the HT will also be an identity. Okay. If say GT is identity, then HT is also, or rather, here. HT is also identity. It's inverse is identity. Everything is as identity. So you can easily see what this amounts to. WT plus 1 is WT minus a constant alpha t. Beta t is 0. Constant alpha into the derivative of the loss with respect to just the IT. IT is basically either a simple index or maybe a collection of indices with respect to which you seek derivative. And then gamma is also 0. Therefore, we're just saying it's WT. That's what the stochastic gradient descent amounts to in this grand scheme. So the second one is heavy ball. Again, heavy ball is pretty much the same, just that the beta has come up. Okay, so I'm going to quickly write this down. The only difference now is that the beta has come up, which means that now in addition to this, you have plus a constant beta into WT minus 1. That's the second one. Okay, that's heavy ball. The third one, nested adaptive. Okay, so we have just moved away from. Let me just write this and then I'll shrink it again. So the only difference now in nested adaptive is that now we are not just adding this beta here, we are also adding to the argument here. It's WT plus something. The gradient is evaluated at WT, right? Plus a. Now there's a beta, the step beta of WT, the same thing. WT minus, WT minus WT1. Okay. So with this, we are done with maybe our more well-known versions. Now we have the new ones, AdaGrad, RMS Prop, and Adam. So I'll probably quickly run through this rudder.io, optimizing gradient descent description. So let's understand the others very quickly here. So what is AdaGrad doing? Well, both. So AdaGrad has this adaptive gradient. It's taking a GT minus 1, adding to that is this diagonal matrix DT. So DT is where the square comes in. Okay. So let's make a note. The DT and HT both involves squares. GT is accumulated. Okay, DT is squaring GT, whereas GT is accumulation. Okay, you can see that GT has an update here. AdaGrad has an update. So GT accumulates. So AdaGrad is where now your kind of adaptation of the learning rate is happening through the square, the curvature of the gradient, the curvature of the function through the gradient square. Okay, so as I said, dt square is being added to gt minus 1. And then the update. So then all of these start mattering. So far they didn't matter, but here you'll find that by virtue of ht being square root of gt, this starts mattering, and so does this start mattering. ht minus 1, ht. So ht inverse into ht minus 1 we discussed in the last class. Basically what we are trying to do is align momentum largely with just the previous updates. We don't want a curvature, a rotation to be effective. Therefore, ht inverse into ht minus 1. Basically, think of it as ht inverse into ht. Okay, so it's the previous version, ht minus 1. So this is like discounting for anything other than momentum. We discussed this in the last class, but you got the explicit effect of gt through ht inverse in this part. Okay, that's the adaptation. So you will start finding that the alpha t is in AdaGrad is alpha. It's fixed. So you're not changing it with every iteration. The adaptation has now come through ht inverse. In fact, that's true with Adam as well. Okay. RMS prop is doing something more. So see, AdaGrad, RMS prop, all of these basically, so RMS prop, in fact, there was AdaMax, whole bunch of these try to fix AdaGrad. AdaGrad says, let me accumulate the squared gradients, but the process of accumulation might lead to very diminishing values of the learning rate. In RMS prop, the idea is that fix a significantly diminishing learning rate created by AdaGrad. Okay, so it said that I won't just keep adding the DTs to GT minus 1. I'll add this convex combination, the beta 2. Some beta 2 has been introduced, convex combination. So that's the slight change. Otherwise, it's pretty much the same as AdaGrad. Okay. What does Adam do? Adam combines the learning rate accumulating the gradient square, the curvature, along with the momentum accumulating the gradients. So Adam is of most interest to us right now. So Adam, I mean, unlike AdaGrad and RMS prop, where beta and gamma both were 0, suddenly in Adam, those are non-zero. Right? So there is some effect that the beta and gamma have started playing in Adam. At least the beta. The gamma is basically, what Nesterov got you. You try to incorporate the momentum within the next gradient update. So especially this part, momentum. So Adam could be thought of as RMS prop plus momentum, or maybe AdaGrad inspired plus momentum. That's it. So Adam is adaptive through RMS prop. It looks more like RMS prop because it's having this beta 2 convex combination, beta 2 based convex combination of GT minus 1 and DT. So you can think of adaptive based on RMS prop plus momentum. Momentum looks more like heavy ball momentum. Okay, so this is basically the overall landscape. With this understanding, unless you have questions, let's move on to the this overview, this blog, radar.io. I'll just highlight some important points here. Okay, so this has a whole bunch. Momentum, Nesterov, Ada delta, RMS prop. As I said, RMS prop is affixed to AdaGrad, but Ada delta was also fixed to AdaGrad. Both Ada delta and RMS props are attempted fixes to AdaGrad. Yes. Slides, okay. Yes. So question is, Adam has this additional component here, or rather division, right? 1 minus beta 2 raised to t, right? And as t tends to infinity or becomes large, then 1 minus beta 2 raised to t will become 1. So it's basically Adam eventually is tending to RMS prop like update. On the GT front, I mean, there's also beta 1 associated with the momentum part. Right? So that still remains. That still remains a difference. So the question being asked is it by design that Adam is meant to resemble like RMS prop? Yes, it is. The only difference is that because you're also adding momentum, you see this has got to do more with initial iterations. So initial iterations, you don't want the momentum to be completely swamped by your update for GTs based on curvature. So it's a more of a detail, but in the steady state, it's attempted that Adam behaves like RMS. Okay. So this 1 minus beta 2 raised to t is for certain stability reasons in the initial iterations. Good question. Okay, sorry, I was on this. I was saying Adagrad had two fixes, Ada delta and RMS prop. We only talked about that. And Adam tries to combine a momentum and RMS prop. That's basically the idea. But there are many others. And you can look at very nice descriptions provided here. Batch and stochastic gradient descent, how they behave, and how did mini batch come up with. And just now I'm just trying to close the story. So momentum, you had the zigzag movement, right? Momentum said, let's try and fix the zigzag movement. If a ball is rolling down a slope, so to speak, right? So ball may have zigzag movement because the path has a lot of stones, pebbles, etc. But ultimately the ball is rolling down, right? So what you're trying to do is capture the major trajectory and not let the oscillations, the minor trajectories, overwhelm the major trajectory. So therefore, you're kind of reminding the ball, oh, you're supposed to go down. Don't get distracted, right? So that's what happens in momentum. Industrial accelerated momentum said, well, let's be a little smart. And that's nicely written. We'd like to have a smart ball, a ball that has a notion of where it is going. So ball has a little look ahead also, where I'm going, so that it knows to slow down before the hill slopes up again. Right? So that's Nesterov updated. Adagrad, as I said, it adapts the learning rate to the parameters, performing smaller updates for parameters associated with frequently occurring features. Okay, so this is an interesting point, which I should just, given this reading, let me highlight it here. So I told you that all these divisions are done through matrix inverse multiplication. So wherever you see matrix inverse multiplication, there's a division. But what is it effectively doing, this division? Right? It's of course looking at accumulations of gradients, but that's one thing. But it's actually also looking at how the features are changing. G, T, J. At the Tth iteration, the Jth parameter, right, we're looking at its gradient. So in some sense, what these adaptive methods capture is the relative importance of features. Okay. So wherever you have the HTs and all coming up, that's the adaptive, Adagrad, and so on. So these capture the relative importance of some feature, right? Let's say with index J over some other feature. With some other index. So that's the basic intention, or another intuitive understanding of what these adaptive methods do. That's been explained here. You're performing smaller updates for parameters associated with frequently occurring features and larger updates for parameters associated with infrequent features. So feature is very frequent. So your update can be small because there's anyways an effect of frequency. Okay, so it's often suited for sparse data. But there's an issue with Adagrad. Adagrad basically can keep adding it. Your effect cumulative alpha into HT inverse. This can become very small in Adagrad. So this part, we say diminishing learning rate. We're talking that Adagrad has, which is it's basically suffering from alpha t into HT inverse becoming very small. That's the issue we are trying to fix. Okay, so that ADA delta, it seeks to reduce the aggressive monotonically decreasing learning rate of ADA grid. That's exactly what I pointed out. Both RMS prop also does that, but these are efforts. So RMS prop does it in a different way. Yeah, stemming from the need to resolve ADA-GRAD's radically diminishing learning rate. RMS prop has also same issue. So you remember we talked about this diminishing learning rates alpha for what other setting? You remember the RMO conditions? Sorry, we had this. What is it? Here. Here you can see RMO 3, RMO V2. Danger, simple tracking that alpha may quickly become very small. They're all related, basically. You remember this? You're able to access this notebook, right? So the RMO line search V2 was trying to fix this issue. Okay, so let's go back to our big picture here. And Adam, what it did, Adam said, let me combine the advantage of RMS prop, right? And ADA delta. So RMS prop and momentum. So it does. So in addition to storing an exponentially decaying average of past squared gradients, it also keeps an exponentially decaying average of past gradients similar to momentum. This is clear now? This is the big picture. Okay. So let's kind of understand one more slide on Adam and then we'll move on. It's heavy ball momentum plus adaptive, not really Nestero, but heavy ball. You could have also a variant, which is I think one of the follow-up variants does Nestero momentum plus adaptive. Okay, so as I said, there are two things going on here. Momentum component is only looking at the gradients, accumulating gradients. Whereas we call it V, but this V is basically accumulation of squared gradients. In a diminishing manner. I mean, you really want too far away history to count less. So that's true with both momentum. There also you'll have in a diminishing manner, but your diminishing is about accumulation of gradients. And then there's another interpretation you can have, which is you could think of the the momentum itself as accumulation of the first order moment. This is the first moment mean, whereas the square gradients, which is where momentum had come up, sorry, the adaptive nature had come up, is related to the second or uncentered variance of the gradients. So if you want to fit a distribution, you want to fit estimate parameters of a distribution to fit the data. Like you try and estimate first order moments, second order moments, or even higher order moments, and try and fit, right? You want the data moments to agree with your model based moments. So in some sense that it's trying to do both. But here we're not talking about data, we're talking about the trajectory of your updates. Okay. So think of this as basically that is of the trajectory of updates. And that's exactly where we began. I mean, this makes most sense because we really wanted to fit something on the trajectory of the updates. This is what we mean by fitting the trajectory of the updates, right? So on the multiple moments basis. So you have a slightly different perspective now. This whole thing, a more refined perspective. Okay, so then there was a question, right? Why do we need normalization by 1 minus beta t? Right, that came in the denominator, the previous slide. 1 minus beta 1 raised to t or 1 minus beta 2 raised to t. So the explanation for that, this part, right? We just see all of these as you find this division. So MT and BT are initialized to 0. And I said there's this issue because both are initialized to 0. They're initially biased towards 0. So if the betas are them, so what will happen? If the decay rates are initially small, you need to normalize by those decay rates themselves to make sure that the decay rates appear bigger than their absolute values, right? So initially t is 0, or I mean t is right. So the denominator will be or t is small, like 2, 3, whatever. The denominator will be large. Sorry, denominator will become small. The overall expression will become large. The 1 upon the denominator will become large. So therefore, you have this normalization by. So just to again, what will this do? Normalization by 1 will make 1 upon 1 minus beta raised to t large. Okay, that's what we have shown here. Okay, so there's some parameter values expressed here. Both beta 1 and beta 2 you'll expect it to be slightly large to begin with. So that as the exponent goes to infinity, then eventually this will also become 0. I mean, beta 1 raised to t will become 0, beta 2 raised to t will become 0. But initially you want to start with a reasonable value. Okay, so this is Adam and very popular. Of course, there have been errors, there have been convergence issues and so on that have I'll probably talk about a little later. Okay. Yeah, so it's in fact it has come up. So there are many extensions of the above techniques. AdamMax is an extension of Adam that uses the infinity norm instead of square norm. So you see we used infinity square norm here, GT into GT, the squared norm here, right? GTJ square. This was a outer product. So what you might want, so what does the squared norm do as against infinity norm? The squared norm looks at almost all the entries with equal weightage. Infinity norm says I'll look at the max entry. So if you want to be somewhat sensitive to noise, robust to noise, sorry, not sensitive, robust to noise, you may want to take the infinity norm. Okay, so that's one variant. In that blog, you'll also find NADM, where you apply Nestor's momentum instead of the heavy ball momentum. So I think I mentioned this, right? So Adam is basically HB momentum plus adaptive. You just make Nestorov plus adaptive, and that gives you NADM. That's it. Okay. Yeah, so then there are other variants, ada delta, where you look at the RMS operator, the root mean square accumulation on weight differences as well. This is a point I made in the last slide. I said that there have been some issues. So AMS grad says there's a theoretical error in Adam because of which it was not converging for convex functions. So the VT may not remain positive. Okay. So it made a fix by which it remains positive. That's it. Okay. Otherwise, I've shown you running through this blog as well. Let's move on. Oh, sorry. Yeah, so the initialization to 0 is more of a recent thing. So the original version of Adam, there were issues with initialization and therefore tending to become negative. So what you see here is a kind of cleaned up version of Adam. This is what you would implement. It's a fixed version. By the way, it's an important thing. The error we are talking about is not just the implementation. There's a theoretical error. So yeah, if someone wants, can pick up this ICLR 2018 paper as a seminar reading as well. Now, very quickly, we look at another direction of analysis of this entire set of work, and that is through regret bound. So you may say, what are the technical tools available, right, beyond what we showed earlier? So convergence result is what we're not covering, but there's this entire idea of looking at an adversarial example. For an adversarial example, what would happen if you had access to the true model parameter as against the model learned for this adversarial example? So that's based on regret bound, which is very common for online algorithms. Again, this is not going to be covered in the class. I'll just run through it. So as I said, there's a paper introducing Adam, had a bug. So theoretical regret bounds are not there for most of them except for Adam, for adagrams. Okay. I mean, if you remember with this RMO conditions and all, we had proper convergence analysis possible, right? That's not always true. And yeah, there was an AMS grad, which I told you had this fixed, right? AMS grad fixed the issue with Adam, the theoretical issue. So it basically used a modified version of Adam to show regret bound. And very importantly, all this holds for convex functions. Okay. So the analysis of convex functions has often opened up the frontiers for advancements, as we have seen so far, whether it's momentum, whether it's adaptive learning, all that has come because of analysis. So that cannot be minimized, its importance.
Excuse me, sir.
So Adagrad is one of the most influential papers of the last. And many numeric techniques that have been improvised upon are based on Adagrad. As I said, Adagrad itself got fixed through RMS prop and so on. But it's still a very important pivotal. The whole notion of adaptive learning rate, for which we struggled hard, in the standard gradient descent paradigm through RMO conditions. It has really opened up that entire space. Right. So we call this, for improved convergence in the case of simple gradient descent. Right. If you look at this movie. So that sense, AdaGrad was a big contribution. Now somebody may say, which is the best of these techniques? I mean, you can't necessarily have a proof that one is better than the other. There are pros and cons of each of these. But there are some interesting takeaways. So, for example, the MNIST data set with a multilinear neural network plus dropout, it was found that Adam, has very quickly diminishing training cost. The one in pink here is Adam. Is doing pretty well. How does AdaGrad or RMS prop? So I remember Adam is basically it's put together two things: momentum, which is the one in red. One in red is momentum. Of course, it's Nestor momentum, and RMS prop, the one in green, which was adaptive. Right, the two have been put together in some sense. Not necessarily momentum, but we've used heavy ball momentum, not Nestor momentum. But nevertheless, it's put together both of these. Now, if you look at the green part, the green adaptive, because it's adaptive, it's like started diminishing quickly, but then after a point, all these diminishing values and all start RMS prop tried to fix the learning rate going to 0 very quickly. But nevertheless, it has issues. The moment you have this adaptive learning rate, you have engineering struggles with the alpha. So, right, the diminishing learning rate. On the other hand, momentum, initially it is not that fast. I mean, it's very slowly catching up. Obviously, right? Because you need enough gradient accumulation for momentum to be effective. Okay, so let's just make these observations, right? You need gradient okay, that's what we see here. Whereas, adaptive, it adapts fast, but then it starts getting slow, right? Okay, and in some sense, momentum has best of both worlds. Okay. Yeah, so the benefits of AdaGrad is that AdaGrad can significantly improve over stochastic gradient descent in sparse feature sets because of adapting. So the whole adapting game itself is because you're able to adapt to the feature space. So that's the key point here. Starts fast by quickly adapting to feature space. The slowing down might be a little bit of artifact of this data set. Okay. So yeah, as I said, because it's looking at the feature space more seriously, or rather because it has a per coordinate learning rate in some sense, it's able to look at the feature space more carefully, almost like a per coordinate learning rate. Remember the entire expression we had alpha t. So what is alpha or alpha into ht inverse doing? So it's basically saying that while you may have a base alpha, the diagonal entries of ht inverse correspond to per coordinate learning rate. But if you have very dense settings, I mean, all features matter equally, right? You don't expect adaptive methods to work very well. The whole advantage is being frittered away. Yeah, in some sense, the learning rate is also decaying. So adding, insult to injury. So then add RMS prop, add a delta. I've all tried to fix that issue because of the issue with Adagrad's learning rate going down. Okay. Also, momentum generally improves upon the non-momentum variance. So if you're accumulating gradients, if you start also accumulating squared gradients, it helps. That's what we are saying. Second order momentum helps if you already have first order momentum. Right? Moment. Let me run the moment. Moments help when you are already having first order moments. Right? First order moments is like gradients. And second order moments is are like the square gradient squares. Okay, so yeah, just trying to re-articulate some important points, learnings.
Past features and previously treatment was treatment features. Meaning the features being not very important. Some features being more important.
Yes, yes. And that's what is happening. So, I mean, if you're finding it difficult to understand, imagine what this would mean, right? If alpha into h inverse, what would that mean? HT was basically like the square root of the GT. HT was square root of GT, accumulated gradients, right? So, what is basically this doing? It's saying that I have this alpha divided by square root GT I for the I component. And when you now multiply this with some other matrix, so let's say this, if I multiply this with a matrix A, so now you are basically dividing each row of that matrix with this entry, right? So okay, so let me then I'm also dividing RHS. Oh, sorry, this is inverse. What did I do? Or multiplying RHS. So you have alpha divided by square root GI. Okay. And GI, again, remember, it's this accumulation of the squares of the gradients. Okay, but also remember that all this is fine, but the generalization is more important than just optimizing the training loss, right? In fact, that's exactly one reason why some of the recent work has shown the marginal value of adaptive gradient methods. So too much adaptation is not worth it. I mean, that's diminishing returns. So there's diminishing returns in overdoing all this. Right? So you're basically getting more complex, less generalizable solutions. Right? And then they also give a synthetic examples where SGD and its variants obtain less complex solutions, but adaptive variants obtain solutions which do not generalize well. So there are a lot of discussions around this, but the generalization becomes difficult if you have very complex updates. That's basically the point. Okay, so this is from the paper, the marginal value of adaptive gradient methods in machine learning. So if you generalize, look at Adam, which has somewhat more complex updates. There's two variants of Adam. One is an Adam with a fix, which I talked about earlier. So VTs never go negative. So this was their observation. And as you can see, as you progress in the epochs, right? The SGD, which is really here, right? The one in black. It started out bad, but then SGD seems to be doing okay. Training error percentage has gone down. You may say this CFA 10, so it has gone down. This is the CFA 10 data set. So, yeah, there's marginal value. I mean, at least you can always show adversarial settings. Sorry. So they're showing that SGD does pretty well as well. The settings in which SGD is doing for all the hard work you do in Adam. Well, Adam has gotten you off to, at least in this setting. Right? I mean, it's getting you to a good start here. Maybe the fix to Adam, the one in purple, I mean, it's better. It's certainly better. But again, the domination of this Adam, fixed Adam, is until a particular point, after which you can see stochastic gradient descent has caught up. That's what they're showing. That's basically the marginal value. There's not so much value all the time. Okay, so look at this. Right, this is training error. This test error. Okay, so training error has got reduced significantly, but look at the gap here. Okay, there are 2 points we are trying to bring up. Momentum. This argument is not against momentum. You can see that momentum is doing pretty well in both cases. So this is about adaptive gradient methods, so not about momentum. And both SGD and heavy ball. So while they are showing some marginal reduction in training errors, the test the gap is wider. Is that clear? Okay. Now, if the training error was very high for SGD or the heavy ball, even eventually, then one might say, well, it's just deceiving us in the training set, right? But that's not the case. It's not deceiving us on the training set. It's doing well. Maybe the gap is not as pronounced, but test the gap is pronounced. So that means it's generalizing well. So did that make sense? That's why the test is shown here on the right hand side. Any other question on this?
Excuse me, sir. Excuse me, sir.
Okay, so there are other readings, marginal value paper I talked about already, but then there's also the ICLR 2018 paper on the convergence of Adam and beyond. And yeah, feel free to go through this blog, which I think they keep updating once in a while. I'm going to just do some extra optional reading, which is not going to be part of syllabus. The whole perspective of empirical risk minimization, regret bound, right? That characterizes analysis in approaches such as AdaGrad. I think I said AdaGrad had this first kind of analysis. So, I mean, a lot of the analysis we did so far was not specific to machine learning, right? So this is, in some sense, when we say empirical risk minimization, this is analysis more specific to machine learning. Okay, so since it's optional, I'm going to be very quick on this. Yeah. The connection of these approaches is also seen through regularization. because regularization is again characteristic of machine learning. So what is the idea of machine learning as optimization? We had a loss function, a regularizer, and we started with a 0-1 loss, NP hard problems. Therefore, we have a surrogate, so perceptron. But then we move on to logistic regression. We have more complex with the sigmoidal neural networks. Okay. So great. The idea in we have seen so far is stochastic methods say, well, why should the gradient depend on the entire data? Take a subset. And I had this big picture. We had collaboratively drawn this big picture. What subset? So we'll come to that soon. But we said, let's do random selection of the points. Let's do random selection of batch of points. There's one perspective which is optimization, but there's other perspective which is generalization. I want to generalize well, right? I want to do well on arbitrary adversarial examples. The two are actually connected. Okay, so there's this pack learning perspective where you're trying to have a hypothesis pack learnable for all epsilon, all delta. When you've seen M examples, where M is omega, right, of the a polynomial in the delta, epsilon, and the dimension of the hypothesis space. An example of hypothesis space might be just the neural networks, the space of parameters. Could be constrained parameters, could be like the non-negative parameters. So the algorithm being able to find a hypothesis H with probability 1 minus delta, such that the error of the found hypothesis is less than equal to the min error, the best error, plus this epsilon. So in such a case, we say that H is pack learnable. Okay. So you want, and this ERR is explained here. This is the expected loss. Often you're dealing with an empirical expectation over the seen data set. So what you do in online learning and regret minimization is for all the example IDs, T equals 1 to capital T. If I consider any adversarial example, X, T, Y, T. So for every possible adversarial example, think of it that way. You want to minimize the expected regret. What is a regret? Well, H star, if I were to obtain as optimal as against the HT obtained by seeing that Tth example, that adversarial example. Okay. So it's, I mean, a regret in common sense. What's your regret that you could not watch IPL, right? So because there was COVID, so you couldn't go and watch something personally. Right? What's the regret that students could not enjoy Mood Indigo? Is Mood Indigo virtual or physical? I'm actually out of sync. So you have a regret associated with every event being online versus offline, right? So had things been normal, you would have had it offline, and now you have a regret associated with that online event. So that's the kind of regret here. H star, if you had access to the all the data, the entire search space, as against now you're looking at through a lens of T, XT, right? So you get generalization in a probabilistic approximately correct setting when that regret goes to 0 as T tends to infinity. So the analysis here is basically now how can you upper bound this expected difference, the regret. So it turns out that this kind of generalization, at least in the stochastic gradient descent, if you want solution that is epsilon approximate with epsilon equals RB by square root T, you will basically need number of iterations T, that is 1 upon epsilon square omega. Sorry, this is omega. Right? But now the analysis is from a different point of view. As I said, this is from upper bounding that regret. Is that clear? So you see that the expression looks very similar to what we had earlier. Things are not drastically changed. Right? So if you want approximation epsilon, then you need number of iterations. But now it's an expectation. The expected. Okay, that's where the jargon has changed. Because the expectation is over all the t's, the adversarial examples that you pick based on which the hypothesis is grounded. Is that clear? Okay, so yeah, so this is like extra optional reading in case you're interested, but we should move on. So I'm moving to the last part before we do subset selection and submodularity. This last component is generalizing this whole gradient descent framework. When you have non-differentiability, when you have constrained cases. I will probably give you some optional reading material in general for constraint optimization, but I think what I'll give you probably will be sufficient to deal with several cases in the constraint case. So what is the idea in constraint case? You're looking at minimizing a function, but you have a constraint, right? This is a constraint. Right? And the constraint becomes here the constraint doesn't matter much, but if you are minimizing under such a constraint, right? If you're sorry in xy plane, your constraint were to look like this. Okay, so if your constraint was something like this, so the minimum, okay, or here, right? So the minimum is going to be somewhere here, sitting in the boundary. This is where your minimum might be. You're not hitting the global minimum, right? Constraint minimum might not be the unconstrained minimum. You see that through the example? And therefore, we'll see how we can generalize gradient descent. And for that matter, even stochastic gradient descent, not a problem. It also has some other applications. For example, if you have non-differentiable components, can you be faster? One more small deviation, we'll go back to representing excess variables as against W. We use W largely because we were trying to look at stochastic approaches. We look at excess variables as than W. Okay, so let's get started. I'm now going to make it a little bit more interactive like before. So let's say I have sum of a differentiable function fx and a non-differentiable function cx. An example I've said is this, right? So summation over I c ix. And what's an example? So let's say I had a constraint C1, another constraint C2. Okay. So IC2 equals 0 if, or rather, IC2x is 0 if x is in C2 and equals to say infinity otherwise. Okay, likewise, I'll say IC1 x is 0 if x is in C1 and equal to infinity otherwise. Is that okay? So that's an example of the C. Now is C, I mean, a summation of the ICIs or each of these ICIs, does it look convex? If the constraints are closed bounded intervals, do you expect this to look convex? Like 0 and then infinity. It's convex. Basically, we're saying that these are 0 and then they become infinity. So 0 in C1 intersection C2 blah blah blah, and infinity otherwise. Is that okay? Okay. F, however, is properly differentiable, has all nice properties you may want. So now, just because C is not differentiable, C is some constraint, will you now put up your hands and say, oh, I can't differentiate? Right? That's the whole point. Can we be a little smart here? You all know, right, that a low rope is as weak as its weakest link. So our ICI is like our weakest link here. But we don't want the whole show to be pulled down because of our weakest link. So this is like our weakest link. Let's look at the strong link. The strong link is fx, right? This is our weak link. But let's look at our strong link. Okay, our strong link is this fx, for which we have so many approaches. Okay, so let's what did gradient descent do? What does it do? I mean, okay, you all say that it does xt plus 1 equals whatever the old boring equation, but some can you give me a different insight? Yes. What is this equivalent to? Can I say, okay, this also is bringing us to optimization. You can always have optimization in parts, in phases. You can have something called bi-level optimization. Any of you heard of bi-level optimization? Optimize with respect to something, then optimize with respect to something else. So could you now think of the optimization on fx through the gradient descent as an optimization problem? Can we think of gradient descent at xt plus 1 was nothing but argmin over x of what? Even in the last class, I said that you could think of the Newton update to be optimizing some Taylor series approximation with certain terms, trailing terms ignored, right? Can you think of gradient descent also similarly? What is gradient descent doing? Yes. Without any reference to convexity necessarily. I mean, you need convexity. Well, you can see if convexity becomes required, let's invoke it. Yes, please come up with your expression. What is it that gradient descent is optimizing? Help me fill up the right hand side. Anyone on the call? I mean, I don't know if I can hear you guys. So after all, it's updating based on some approximation around xt, right? F of xt is there. But plus what? If I give you some more terms, okay, so you have to help me fix the other one, right? So this looks familiar, this part from convexity. Obviously, this cannot be sufficient, right? If you try and set the gradient of this with respect to x to 0, something's wrong. Okay. You don't get any term involving x at all. So I would expect one more term to be put in there. A quadratic term. I already give you a hint, right? Some Taylor series approximation with some truncation. So what if my quadratic term involves not just x minus xt, but norm of x minus xt square? Now, what would be, so yeah, I'm going to leave you with this. What will be the scalar here? Give me some scalar here. Help me fill up the scalar. Pen and paper will help here. So sorry, 1 by 2 gamma. So that's a suggestion, 1 by 2 gamma. That's straightforward. You take the derivative of this with respect to gradient with respect to x. So you basically get 1 upon gamma. What's the gradient of x minus xt norm square? Will be what? Yeah. So x minus xt. This f of xt will is just a decoration. It will get anyways go away and you take the setting. You get this plus. So you always bring x gradient transpose times x as x transpose the gradient. So the x will go away. So you'll basically get plus gradient f of xt is 0, which basically means that x is xt minus gamma times gradient of x, right? So I'm going to know, based on this observation, I'm going to know prompt. Could we have viewed this optimization differently? Instead of trying to do everything in one shot, can I now break it into parts? I'll ignore Cx. Look at what is this? This is the quadratic approximation to the function, right? So I'll look at quadratic approximation to the function, minimize it, and then bring in Cx. Can I do it in parts? Okay, a lot of optimization is about that. We'll see some examples of bi-level optimization. In fact, we did bi-level in the midsem also, right? Midsem we had lambdas and x. No, you forgot. In midsem we had lambdas and x, right? We said so there are two components to the optimization. Okay, so this entire thing, again, I'm telling you, this entire thing, or rather this component, is a quadratic approximation 2f around xt. Okay, so this is exactly what we have brought up here, a quadratic approximation. But now what I'm going to do is, instead of now just doing a gradient descent update on this part, I'll take the quadratic approximation. Onto that, I'll slap on my Cx as well. Why? Because my function has now become simpler, right? And moment I write quadratic approximation, I mean that I'm doing a gradient descent implicitly, right? But here I'm going to I'll add on slap on Cx and obtain the next iterate xt plus 1. You may be wondering why. What is the advantage of doing all this? I think it's best explained when you have a motivating example. So I'm going to take some motivating example. But if you have any questions here, let me know. Okay. So imagine, okay, let's take a motivating example. Say Cx is the one norm of x. Okay, lasso. But this is after slapping on my first order approximation to the function. Does this become any easier? Does this simplified formulation based on first order approximation around xt help? And it's best to take this discussion forward and see an example. Okay, we'll be seeing this example. The other thing I have done. Okay, so before I think I jumped a bit too much. Let's also reformulate this. A reformulation would be helpful. Let's reformulate this. What I'm going to do is f of xt. If I try to minimize this entire expression with respect to x, f of xt doesn't matter. Right? So I'm going to cancel out. Write this whole thing differently. Now, the moment I see something like this, squared, x minus xt squared, norm squared, a term like this, from your experience with analyzing convergence, are you tempted to do something? Sorry? Telescopic summing is, no, not telescopic summing. That's telescopic summing may not be useful here directly. But we used to do one more trick. What were the 2 or 3 or 4 tricks, whatever we learned? Just list them down. By elimination, it's not telescopic summing. What's the other? What are the other tricks? U transpose V, we wrote it as some norm square. So completing squares. Can we complete some square here? Can I write this as, so I'll remove this, but add something to complete a square? What square will I complete? Gamma? The norm gradient square. So the suggestion here is to take gamma square into norm gradient square, right? Add that. Of course, adding it. So remove this, but add this in place. Let's see what happens. Let's simplify. What happens? What do you get? x minus gamma by 2 times. Oh, gamma square by 2. Only gamma by 2, not square. Yeah, because there's already 1 upon 2 gamma here. Okay, so let's try doing this. So let's say I take 1 upon 2 gamma outside. Right, then you'll have gamma square plus a 2 gamma here. Right? So if you want, I'll write the whole thing. Make it easier for you. So you'll have gamma square norm ft square plus 2 gamma of this dot product plus norm of xt x minus xt norm square. Whole thing plus cx. Now, is there a way we can write this first term as a square, 1 upon 2 gamma times some square? What is that? Yes. Is it plus or minus? Okay. Okay. So I'll write it as norm of x plus, x minus xt minus gamma times. Right? It's minus minus plus, right? So cx is just hanging around. Nothing special about it. This is okay. So what is this basically? This is saying that argument over x of the difference between x and the gradient descent update, the whole square, plus cx. Okay, so that's what we are showing here. This is what we got. In plain English, what this is looking at is squared norm difference of x from the gradient descent update. That's what this part in red is. So it's called a proximal step. Okay? And I'll show why this proximal step is required through an illustration. Oh yeah, thanks. I mean, and thanks for reminding. I'm going to leave you the homework. So this, so let's consider the homework. Recall a case of Cx equals 1 norm of x. Okay. And I want you to recall the steps we had written for lasso. So that's very timely for the homework. So lasso, it requires you to brush up. Otherwise, you might get lost if you don't brush up. So please brush up. How we solved a lasso. What did we solve in lasso? Can you remind me? We'll end with that. We spent a lot of time writing down the subgradient, setting the subgradient to 0. Or rather, wrote necessary condition. Was it necessary or sufficient? I think it was sufficient condition, right? Sufficient condition for lasso. What was that exact expression we had done as homework? Recall f of not homework, as past work. We had done this, right? F of w is 1/2 norm of w minus y square plus lambda 1 norm of w, right? We had written these steps. And we had this soft thresholding operator, you remember? S lambda y equals yi minus lambda if yi is greater than or equal to lambda, and 0 if yi was between minus lambda and lambda, and it was yi plus lambda if yi is less than or equal to minus lambda. Recall this. So can we make use of this for now completing our lasso? Completing our iterative soft thresholding star. Right? All we need to do is do the proximal. I mean, and we want to invoke this in the proximal step. Okay. So that's homework for you. So in homework, we call the sufficient condition test for lasso, simplified lasso, and plug it in the proximal operator here to complete our star algorithm. Okay, so with that we'll end today. Thanks.